Thank you very much. Well, that brings us to the end of the hour. Join me in thanking Rajiv and Pankaj for excellent talk. Silent
Thank you.
clap.
Thank you very much for having us.
At this point,
Bye.
I'll hand it off to Bei Yu. Thank you very much, Bei.
Okay.
Thank you.
Thank you.
Okay,
Bye-bye.
thank you. I guess it's time for us to start the technical session today. Today, the session 3, the title is Machine Learning for Reliability Improvement. For each talk, in total, we have 5 presentations. For each presentation, in total, we have 15 minutes. So I'd like to pass time to the speaker of our first technical paper today, data-driven fast TDDB agent analysis. So the speaker will be Shaoyi Peng. Hello, Shaoyi, can you share the screen with us?
Yes. So am I audible and can you see my screen?
Yes.
Okay, sounds good. Hi everyone, my name is Shaoyi from UC Riverside. Welcome to the short introduction of our work, data-driven fast electrostatics and TDDB agent analysis. So this work aims on analyzing the lifetime from TDDB. And the TDDB itself is a failure mechanism at the back end of the line. An example you can see is on the right photo here. It appears as a conducting path or short circuit between 2 copper wires. And to evaluate the lifetime from TDDB, normally we need to get an idea of how strong the electric field can be around the copper wires. And with that information, we can calculate an integral around the copper wires and get a basic idea of the lifetime of wires. So the idea here is the calculating of the electric field is essential for TDDB analysis. And on the other hand, here's another background knowledge of TDDB analysis. Because the layout is very large, in order to get the electric field information, we can analyze them piece by piece. So in that way, we avoid calculating the whole layout in one shot because that's impossible. So with the help of this, we can model our problems with a fixed size of layout pieces, and we apply voltages of VDD and the ground to 2 sets of wires. So here's the problem shown in this figure. With tools such as COMSOL that uses finite element methods, we can get the voltage distribution out on this piece. With the voltage, we calculate the numerical gradients, and then we can get the electric fields, which is shown in this figure. And of course, with the electric field, we can continue with the TDB analysis to get the lifetime of each wire. So that's the goal we want to reach. And the observation here is with the help of layout partition.
Joseph, can you hear me?
Yeah.
Hi, Joseph, can you hear me? Oh, maybe.
Yes.
Yeah, I'm trying to switch from the conference to this. Please give me.
Okay, I think I will just continue. So the point I'm trying to make here is in TDDB analysis, the sub-problems we are trying to solve is fix the size the layout pieces, and some of them are VDD wires, some of them are ground wires. So we can actually see this as an image transformation problem. The output we want to get is the image of voltage distribution here. And the input image, we can encode them with 2 channels, basically a ground channel and a VDD channel. We just give a value 1 to where those wires are and 0 out all the other spots. So like here is the example of our input image and output image. we just expect a surrogate model to do this. And of course, we apply CNN to this. We use a model that looks like this, that is composed of an encoder part that shrinks the size to 1 by 1, but with higher dimension, and followed by a decoder that takes the bottleneck layer back into the output image. And the result of our model is pretty good in terms of the voltage, which is the direct output of the model. The voltage we have is the range is just 0 to 1 volt, and the RMSE we get is around 1% of that range. And the following steps, as I discussed previously, is then taking the numerical gradient to get the electric field, and then continue with the TDDB analysis. So in terms of the accuracy of the electric field, it is the accuracy is not as good as the voltage, but still acceptable. And the most important part still of this work is TDDB analysis. So we take the information of the electric field and do TDDB analysis on some sample wires. We get that the accuracy is, the difference or error is below 8%. And of course, in terms of speed up, we get around 138 times speed up compared to console. And a point I want to make here is that the machine learning method is more friendly to parallelize it. And as we discussed, the problems we get here is partition pieces. So in order to analyze the lifetime of a given layout, we actually have a lot of pieces, a bunch of problems that are the same. So machine learning is very good in taking all that, because it can take a batch of inputs and generate a batch of outputs. However, for traditional methods like console or other tools, they can just only do that 1 by 1, because the parallelism is hidden in the tool itself. So to summarize our work, we aim to accelerate the TDDB analysis. The reason we can do that is the core problem of TDDB analysis is analyzing voltage and electric field information on a fixed size of layout piece. And that itself can be viewed as an image transformation problem. We apply CNN-based neural network to accelerate it. We get accuracy with errors below 8% and around 138 times speed up. All right, that's the end of my presentation, and thank you for your attention.
Okay, thanks for the presentation. So ladies and gentlemen, if you have any question, please you can raise the question in the Slack discussion group. Also, you can directly type the question in the chat room in the Zoom. So let's see whether we have any question from the audience. Let me ask a few questions. Basically, 2 questions. The first one is about the scalability. I see the input feature size is 255 times 255, which is very typical in computer vision application. But for the layout, if it's very huge, then would you scale down the layout into this kind of size, or you would do the partitioning?
Yes, partitioning would definitely be a key step in this. The input, as I said, is just a small piece of the layout. A example is like shown in this slide. It's actually much smaller, but here still, in this work we use, I mean the length of 1 pixel is larger than a nanometer, because we get the pitch or feature size of a given technology. So in this work, we use a technology that has a feature size of 60 nanometers. So I just use a 60 nanometer for the length of each pixel, and that can well capture the information of every copper wire we get in the layout.
Okay, and after the partitioning, the whole layout will be clipped into a bunch of the regions. May I know whether all the regions have overlapping or not?
Sure, we will partition them in a way that is overlapped, because the idea behind this partition is the areas that at the boundary may not be accurate. So we leave the room for some overlapping in order to get correct information back onto those regions.
Yeah, understood. And then basically for one region, they may have two different estimations in different clips. Then how can we merge them or fuse them together to generate the final the analysis?
It's like we can pre-assign a region of that we deem accurate, and the rest that we deem are inaccurate for a given piece. Let's just take an example of this piece. Let's say it is a 100 nanometers long and wide, and we can say the inside 80 by 80 is accurate, or that's just a pre-assumed number, and we can we have the rest areas that are inaccurate, and in order to get those areas correctly, we move this tile to the next part by 20 nanometers. So the overlap between the two partitions can get the accurate results back to the as compared to the first tile. The point I'm trying to make here is actually a region that let's suppose we are just interested in one point, and that can appear in multiple pieces, but we can control it so that it only appears as accurate in one piece.
Okay, I can see your point. So let's see whether we have any other question from the audience. Actually, another general question for all the machine learning application is about the generability. So can you have some comment on this one? Say how you split the training data set and testing data set, and how difference between them regarding the feature size or feature.
Sure. I think a good point about this work, maybe not a good point, I mean an easy point for this is we are targeting synthesized layout pieces, and the patterns of all the wires are generated by physical design tools. So and the pieces are very small. So to complete this project, actually we only have one design, and I have a figure showing how the data set is partitioned in the longer presentation, but the idea is we split it by the Y value. So just let's say the upper 20% of the layout goes into the training set, and followed by the next 20% goes to the validation sets, and the rest goes into the test sets. And of course, there are no overlaps between the sets. And we expect that the small pieces in the regions will capture the patterns that could be generated by the physical design tools well.
I see. So basically, you are doing a speed up for one particular design. Yeah. Another following question is why you split them into the training, validation, and testing. Why don't you merge the training and validation part together and try some cross validation? so that the training set can be enlarged?
Because the sample of this partition is quite small, so a layout itself can give us a big enough data set. So
okay. 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 Due to time limit, maybe we can move to the second presentation. The second one will be presented by Jinwei Zhang, talking about Hotspot-Aware task mapping for lifetime improvement of multi-core system using deep reinforcement learning.
Hi, can everybody hear me clearly?
Yeah, we can hear you. Thank you.
Hi, everyone. I'm Jinwei, a third-year PhD candidate at the University of California, Riverside. Today, my presentation is titled HAT-DRL, Hotspot-Aware Task Mapping for a Lifetime Improvement of Multicore System using Deep Reinforcement Learning. As we know that in recent years, there are many dynamic thermal or reliability management methods proposed, such as task-to-core mapping strategies are extensively studied with deep learning these years. However, the limitations of these existing strategies are also obvious. Firstly, most of these strategies mainly rely on the thermal sensors, but ignore the stress of the hotspots. And in our study, we show that the stress of the hotspots are actually closely related to the specific workloads. Oh, can everybody see my video?
No, yet. Okay.
How about now?
Yeah, we can see you.
I'm sorry, I didn't turn on my video at the beginning. And here I want to show you a concrete example that how the thermal sensors can confuse these existing strategies. For example, we have a upcoming task to be mapped. And at this point of time, all of the cores are having the same temperature, for example, 90 degrees. So most of these existing strategies are not able to differentiate the thermal status of the cores. But however, if we know the power knowledge of the full chip, for example, we know the power of the hotspots of each core. And if we know the upcoming task will activate the hotspot B, for example, then we would say it is likely that this core would be the best choice for mapping this task. So in this way, the power distribution and the stress of the hotspots can provide us much more information to do the task mapping. Enabled by our thermal imaging system, we are able to capture the full chip thermal images of the processor. And based on our recently proposed algorithm published in date 2020, we are able to convert the thermal information into the full chip power information. And this figure shows the scattered power hotspots of the full chip, in which we can see that there are primarily two clusters of the hotspots with each core. And in the test, we were using the Intel i7 quad-core processor. And so this scatter is after we have run a set of Pharonics benchmarks. So we identified that there are two major hotspots for each core. To prove that the hotspot-aware scheduling indeed has a positive effect for the multi-core system, we conduct a simple motivation experiment. In the first setting of the experiment, we assign two tasks named hint and the postmark on two cores of the processor. So the task will run on each core without migration. And in the second setting, the two tasks will swap the core every other interval t. So every other interval t, these two tasks will swap the cores. In this way, each core, the two hotspots will be stressed more evenly than the first setting. So this is called the hotspot-aware scheduling. And the results of this motivation experiment shows that there is always a temperature reduction, even though it's not very big, just 1 degree temperature reduction. But this temperature reduction always holds in our repeated experiments. And notice that this experiment is conducted when the processor has a active cooling. For mobile systems or which has passive cooling, this temperature reduction may be bigger. And also the execution time actually is a little bit faster than before. So we want to say that the performance has not been degraded at all, even though we do the migration. So the migration overhead can be ignored. And in real-time application, we know that we cannot use the camera forever. So we proposed a model that can tell us how much the task will activate each of the hotspot within a core. So the model is a very standard, fully connected 4-layer neural network, which takes in the vector of the performance counters, and the output would be the ratio, the normalized ratio of the power activation on each of the hotspot. These two diagrams shows the results from the prediction model. So we can see that the model can characterize how much the task will activate the hotspot compared to the real experiments. And finally, we can build our workflow for this whole scheme. So we use a different reinforcement learning scheme. Here, it has environment and the states and rewards, agent, and also the action. In the environment just is the processor, basically the processor running a few workloads. And in the runtime, we sample the online PCM data, so the performance counter data of the processor. And we also sample the online temperature. And here we have the hotspot activation estimation model, which I mentioned before, like this. It can calculate how much the hotspot has been activated. And combining these two information, we can formulate the threshold voltage shift induced by the MBTI and HCI effects. So MBTI is a negative biased temperature instability and the hot carrier injection. These two thermal effects, they will mainly affect the threshold voltage shift of the semiconductor. And also we can form the thermal agent of the hotspots, which is closely related to the lifetime of the whole system. And the states is continuous and reward continuous. For the agent, we use the recently proposed learning algorithm, which is called the soft actor critic algorithm. This algorithm is kind of similar with the algorithm that another attendee used in an earlier session. And after the agent outputs an action, the agent will overwrite the system, the OS scheduling information. For example, set up the CPU mask for the workloads to actually migrate the tasks. So this is the whole workflow. Here I did not show you the mathematical formulations for each of the state or action. If you want to know the mathematical formulations, you can look at my complete video or look into my paper. Here I'm presenting the primary results for our algorithm. So the first figure shows the improvement of the mean time to failure. For each cluster, these are the lifetime, the MTTF for each core, from the core 0 to core 3. And we compare the results with the Linux default and the non-Hotspot-Aware scheduling. And the green bar means the proposed HAT-DRL algorithm. The worst hotspot, the lifetime of the worst hotspot will determine the lifetime of the core, And the lifetime of the worst core determines the lifetime of the system overall. So in this diagram, we can see that the proposed algorithm can achieve about 50% and 160% longer lifetime than the non-Hotspot-Aware and the Linux default scheduling, respectively. And these two figures shows the voltage the threshold voltage shift under our proposed technique and the non-Hotspot-Aware mapping. And we can see that by using the proposed technique, either the peaking of the threshold voltage shift or the overall range are actually very well mitigated. For the non-Hotspot-Aware mapping, which means the algorithm only applies the thermal, the temperature measurements without considering the hotspot stresses, we can see that the peaking and the range of the threshold voltage shift has a very big oscillation. For this figure, it shows the increment of the agent under the Linux default scheduling and the proposed algorithm. We can see that for the proposed algorithm, the increment of the agent is increased very gradually and evenly. But for the Linux default, it increases very quick because for a long time, the Linux can, for example, assign the tasks on the same core for the long time, and thus stresses the same hotspot for a very long time. But by using our proposed method, the hotspots for the full system can be stressed very evenly. So each hotspot is stressed very evenly. Thus, the worst hotspot can be mitigated. And now let me summarize our proposed method. So firstly, we explore and take advantage of the deep knowledge of the hotspot stress information of the multi-core system. And secondly, manage the tasks such that the hotspot are to be stressed and aged evenly. So in this way, it will in return boost up the full chip thermal performance and the reliability. And at the last, the lifetime can be well extended and the reliability in terms of threshold voltage shift and also the MTTF can be improved as well. So this is pretty much my presentation. And for detailed information,
do you have any question from the audience?
Yes, I would have a question if I can ask.
Sure.
Yeah, so first of all, thank you for the nice talk. I'm Christian from TU Dortmund, by the way. So you proposed this concept that you're estimating the influence on the thermal hotspots with the surrogate function you trained on the neural network, right?
Yeah.
I think this, yeah. And then basically, yeah, exactly. It was the slide 7, I guess, this neural network. And then you execute this reinforcement learning agent based on the information coming out of this prediction here, right? So my question is, what is actually the cost of using the prediction? I mean, in the maybe unrealistic but optimal case, you would just have your setup where you can precisely measure the hotspots currently in the CPU, as of course this is not normally possible, but in the perfect case, you would just have this information. So have you any idea how much better the reinforcement learning agent could perform with the real information? So what's the cost of being forced to use this estimation here?
Here we use this neural network model to estimate the power hotspot, to estimate the power activations on the hotspot, because the primary reason is that in real-time application we cannot use the thermal camera forever, right? So to train this model, we have the real measured information from which, based on our thermal imaging system, and we can really measure the power activations on the hotspots. So these are real measured information based on this data. Based on this data, we can train this model. So there are two neural network models. The first neural network model is estimating the power activations, and the second neural network model is for the reinforcement learning model. For the cost, you mean the time cost or?
No, I mean actually only how precise. What's the error of the models you trained there? How precise are they?
For example,
do they well estimate the activation of the hotspots, or is there any drift increasing over time?
The accuracy is pretty high. One of my lab mate helped me to train this model. The accuracy, which you can interpret from the result figure, that it actually tracks the real measurement, the history very well.
Okay, thank you.
Yeah, did I answer your question? I'm not pretty much sure.
Yeah, a following question is that in your motivation example, you do the swapping in every new interval. Have you considered the data transfer, especially the cost of power consumption during the transfer between the cores?
Well, so for this experiment setup, we set the interval to be 10 to 20 seconds because here the benchmark that we use have a very long time of execution for minutes, and sometimes the benchmark can execute for hours. So we set the interval to be 10 to 20 seconds. Is
okay. Got it. That's reasonable now. Okay, due to time limit, we have to move to the third presentation, which will be presented by Kristen, talking about the aware memory allocation. Okay, so Kristen, I pass time to you.
Can I just share the screen now? I guess, yes.
Hi, I'm back.
Hi.
Hello, stop sharing.
Let me stop share.
Okay.
To be honestly,
I hope you can see the presentation now.
Yes.
And hear me well. Okay, thanks. Yes, hello again. I'm Christian Hakert from TU Dortmund University, PhD student at Professor Jian-Jia Chen's group. And I'm highlighting this paper, Can-Wear-Aware Memory Allocation Be Intelligent here? And what we tried to answer in this paper, kind of this question, if where memory allocation can be done with reinforcement learning rather than a carefully handwritten strategy. So this is not talking about the deep hardware level, but rather the system software level, maintaining actually during runtime what is happening with your hardware. And if you think about, you have a system with non-volatile memory, and this non-volatile memory has limited write endurance. You carefully have to watch out how many write and read accesses you perform to which region of your memory, because if you don't carefully watch out and perform too many accesses to a certain region, your memory will just die prematurely, and you can do way better if you distribute your accesses well over the memory. And how this usually is done in practice is that you have your memory, which I tried to illustrate here on the left side. So this is just memory space, and you split this in some sized block regions, and for all these regions you observe the memory age during runtime. For instance, you can do this by counting how often the memory is written and read at this different sections. So this is the input you get here, and then you define a set of actions, which could be to use logical to physical memory mapping and remap the physical location of some memory contents here, or this could be in the context of memory allocation to define a certain target of malloc requests to, for instance, target them to cold or hot memory regions. So you usually have a certain action space here, and then you need this connecting strategy in between, which, for instance, could be always swap the hottest with the coldest page, or which could be, as I mentioned before, always allocate new memory requests to the coldest memory space, to the coldest free memory space. And as I said, you can design such a strategy by hand, but as we saw in some of the interesting and great talks before, that reinforcement learning could also be a good candidate to replace this handwritten, carefully designed strategy here, because if you do this by hand, you never know if it's good or if it's just working for your applications. And if you just let the reinforcement learning agent do this, it will adopt to the current application you're executing there, and you have a dynamic solution. Okay, towards this, we first need to set up the system. So the technical system, then defining which actions and state space our reinforcement learning agent can get. And in this paper, we proposed, therefore, to use virtual memory. And this is where we have a logical perspective on the memory on one side and the physical perspective on the memory on the other side. And we have an arbitrary interchangeable mapping between this logical and physical perspective. And then at any point during execution of the real system, this mapping can be exchanged. This will change the position of logical memory context in the physical memory without changing the application's view on this memory. So you don't need any cooperation from the application. It can be fully done in the system software in the operating system. So the drawback of virtual memory here, if it's realized with a classic MMU, you're usually limited to 4 kilobyte page granularity, which is a bit coarse for fine-grained memory allocations, because what applications usually do is allocate some integers on the heap, and then the granularity of 4 kilobyte is just a bit coarse. And therefore, we proposed another concept in this paper where we actually split virtual memory pages into further sub-pages. So this is a virtual memory page, these black surrounded blocks, and we split this into a smaller number of sub-pages. And then how we can combine this to an arbitrary mapping still is we take multiple virtual memory pages, like indicated here, and map them to the same physical memory page, which allows us to overlay, even by the use of virtual memory with the memory management unit, overlay the physical and virtual memory so that we can somehow arbitrarily still map the smaller sub-pages to physical locations. And this intuitively already defines the action space for the reinforcement learning agent, because whenever a memory allocation request comes in, this has a certain index in the logical memory space, and the logic address will not change. And then the reinforcement learning agent at any time can decide to just trigger an action for every logical memory block, and this action will replace the physical position of this memory block to the next fitting free physical memory location. Okay, so far so good. So the question is left to answer how the state description and the immediate reward description comes in, as we are using Q-learning here. This directly goes into the agent description. And for this, we just take the information we have from the logical and physical memory perspective. So this is inside of our system. On the one side, we can determine the age of the physical memory perspective just by counting how often which physical memory region was written and read. But we can also count the age of the logical memory perspective, which basically can be inferred from the same number, but just needs to reflect the mapping from physical to logical memory pages. So this carefully needs to be adjusted whenever the mapping of logical to physical memory is changed. But then basically, we can, on the one hand, count the age of the logical perspective, on the other hand, count the age for the physical perspective. And this, on a somehow simple way, allows us to encode the mapping from logical to physical blocks into the state description from the reinforcement learning agent, and therefore also deliver the chance for the agent to decide which logical block should be mapped to which physical block, or is currently mapped to which physical block. Okay, then given this information, it's just Q-learning here, and it decides for an action which should be performed in the system. This action then is passed to the system, will influence the mapping of logical to physical memory pages. Yeah, and then this just happens during executing the full application during runtime, and it will influence the mapping and therefore increase the memory lifetime, hopefully. So we evaluated this on a set of benchmark applications, which are memory allocation benchmarks. So we take them, took a simulation from them where we actually implemented our agent and had a look on how they are writing the memory, how they will write the memory after the agent performs the remappings, and then what is the final memory lifetime. So what we did here as the immediate reward, we always provided the agent the current status of how well leveled the memory is. So the ultimate goal of the reinforcement learning agent here was to increase the current wear leveling, which also indicates the total lifetime of the memory at any time. So we can report two things from our evaluation here. On the one hand, we see that the agent we propose in this way actually works and reacts to the application-specific properties. We compared this to a naive implementation of a strategy and to a random implementation of a strategy. And in some of our tests, this was actually outperformed by the agent by a good ratio. But what we also report as a challenge here is the initialization of the agent, because as I said, this is all done during runtime. The agent is just initialized and started together with the application without having at this moment any knowledge about the application, and therefore cannot make somehow meaningful decisions at the first glance. And if the application does not run for very long time, it is a hard game for the agent to actually learn enough about the application to do the application specific remapping decisions. So we observed here in our evaluation that the longer the agent was able to observe the application, the better the results get. And this leads us to the remaining question we leave remaining open for further discussion, how the initialization can be done for relative short-time applications. So possible ways would be here to get some pre-profiled knowledge about the applications into the agent or something like this. So this is a bit of unanswered question right now, how this initialization in a realistic setup can be properly done. So this is it for my talk. I'm happy for your questions now, and thanks for your attention.
Yeah, thanks very much for the great talk. Let's see whether we have any question from the audience. I actually have one question that relates to the reinforcement learning. Can you describe the action in your reinforcement learning framework?
Yes. It's somehow a bit slow, but yes.
Oh.
So the idea here is that we have unique identifying numbering of the logical memory blocks, which are on the one side present in the state description at these indices, and on the other side just are reflected in the action action description, so that somehow a relation exists from the logical aging of the memory chunks to the action which should be performed.
Okay, yeah. So can you have some more? Do you have any comment whether this kind of action can cover all the relocations design space?
Whether it can cover the entire space, or what was the question?
Yeah, let me figure out later. My second question related to the reinforcement learning is that currently the reward cannot be obtained immediately. We have to wait a few actions to obtain the reward. Do you have any comment how we can resolve this kind of challenge?
This is actually somewhat very easy resolved here, because we use experience replay for our implementation of the agent, which means we don't immediately train on every sample we get in there, but we store samples for a while and then just train on random sampling of this replay buffer. And this just delivers us a chance to wait for the next time step until we have the aging information and put this all to our replay buffer and then later train on this.
Interesting. Okay. Yeah, I will check the details in the paper to see how this kind of the long term.
So, this is Jian-Jia Chen, so I'm co-author of this paper. So the short answer to your first question is that we define a few allocation strategies in the actions we can do. So this does not cover all possible allocation design space, because encoding all of them is probably too much to do that during runtime. So only a few strategies were encoded in our agent. Yeah, and the details are in the paper. Okay.
Yeah, I was very thanks very much, Jian-Jia. Okay, due to time limit, we can move to next presentation. Next one will be delivered by David Winston from IBM, talking about the machine learning model for the year analysis.
All right. Can you hear me all right?
Yes. Yeah.
All right, let me share my screen. Okay, great. All right, thanks everybody for attending. My name is David Winston. I'm a senior engineer at the IBM EDA organization, and I lead the circuit simulation team. And I'm going to be talking about our machine learning model that we use for an adaptive Monte Carlo yield analysis. We sort of came into this project a little bit by accident because we got a call from one of our senior design leads saying, you know, we'd like you to take a look at what we do for yield analysis. There had been a lot of work done with importance sampling, and we'd like to kind of move beyond what some of the tools do with importance sampling and look into sort of other capabilities that people have done with machine learning. So we took a look around and tried to understand sort of what has been done, and talked to a lot of our designers and asked them specifically what they want. And so the real problem that we're trying to address is we'd like a tool that could seamlessly move from kind of regime to regime when it comes to estimating failure probabilities. So given like just an arbitrary circuit with some kind of arbitrary type of parameters, it could be some kind of process conditions, temperature or voltage, could be some kind of circuit pass-fail threshold, different kinds of test criteria, or changes to input stimuli. A designer may not really know like what is a given failure probability going to be. And what we really liked was a tool that could kind of work and adapt regardless of what the kinds of criteria the user set up and really what kinds of failure probabilities they might expect. So we didn't want the user to kind of think about, well, how many samples do I want to run for my Monte Carlo analysis, or what kind of technique do I want to use? The designers really just want to specify a variety of different kinds of measurements. And so, for example, taking a cross-section from our arrays, looking at the performance of bit cells in addition to sense amps, and looking at them sort of independently, but also in sort of conjunction with each other. They want to be able to specify different kinds of measurements all in the same run and not really worry about what is the failure probability going to be and what kind of technique should they use. If it's relatively high failure probability, meaning it takes a few number of samples to estimate how rapidly the circuit fails, then you can get away with just doing straight Monte Carlo simulation, Monte Carlo analysis. But as you move up the sigma range, you discover that, well, you really just don't have the processing power to do all of the samples that you really need. So we get into the machine learning realm, and that's where I'll be focusing today. And then you get up beyond 6 sigma, and then it really requires modified sampling techniques because you just cannot, process the raw number of samples required. So we're focused on machine learning, and we wanted, since we knew that we were going to build a tool, or the designers were asking for a tool that could adapt to any kinds of different kinds of measurements, we really needed to figure out, well, what is a way that we could build our machine learning models, separate the training steps from the actual Monte Carlo sampling analysis and when we're actually doing inference, and and build a model that would allow us to reduce the numbers of simulations. And that's really the key, is we're not generating results that are strictly based on the result of a model. We're using the machine learning models to guide us as to whether a simulation is necessary. And so what we do is we use a support vector classifier or support vector regression. I'm going to be focusing on binary criteria, so we're just going to focus on support vector classifiers. And we train it using a uniform sampling of all features. So the features in our model are the sources of statistical variation modeled in a net list. So these could be things like mobility parameters on a per transistor device, per transistor basis. It could be threshold voltage. They're very global process parameters. And so anything that is modeled in the net list, it's typically modeled with a normal Gaussian distribution. But we're just, during the training during the training phase, we're just looking for when does the circuit fail? Under what conditions does it fail? And so we're training our model such that we have a good understanding of where the pass-fail criteria, pass-fail boundaries actually exist. And we are assigned a score. We kind of normalize this whole process so that we can, easily move from design to design and, process condition to process condition. And we have a score that's basically a measure of how far a particular sample is away from the pass-fail boundary. And scores that are positive are considered passes, and scores that are negative are considered failures. But we then take that support vector classifier and use it in a second stage to then add some enhancement samples that are predicted to lie near the pass-fail boundary, but that we're going to simulate and use as additional training data so that we have kind of a better understanding of where does the circuit pass, where does it fail, and then use that during our Monte Carlo sampling. And so here's kind of one of the main keys, is we simulate all predicted failures and we simulate some predicted passes, because we always want to verify that a failure actually is a failure. But we want to keep an eye out on our passes, our passing conditions that's predicted to pass, and verify those that might actually be failures. So we know, okay, so we have this model, and now we enter into the Monte Carlo sampling. And we know that the model is not always going to be accurate. And so we have to adapt to the mispredictions. So what I'm showing here is a histogram of all of the scores for a particular test case for a particular circuit. And it's basically saying, look, all of the scores are basically passes, and which is what we want because it's a very low failure probability. We have lots of circuit samples with all these different sources of variation. 99.999% of them are going to be passes. What we're trying to pluck out of this distribution is these samples way down at the bottom left that are failures, but they could also be potential failures. So we have to we sort of develop this scenario where we not only simulate things that are predicted to fail, but we cache samples that might be potential failures. And we look at the mispredictions to kind of guide us, well, how far into this passing histogram do we have to go to see if there are any failures? So just as a couple of quick examples here. So I took a cross-section from one of our array designs, and I ran it with sort of a nominal voltage, and we just kind of do straightforward path delay through, I think it's like 4 or 5 stages. Not a particularly large circuit. It was something that I wanted to be able to simulate very quickly, just for kind of comparison purposes. But I kind of set it up such that it had a relatively reasonably high sigma, but not something that I couldn't simulate entirely. So as I mentioned before, I'm not asking the user to kind of decide how many simulations to take or anything really about the running of the Monte Carlo analysis. They're just setting up their criteria. And what you see here is two cases of total amount of cases I took is about 4 million or 4.5 million cases. And again, we're looking for these few failures. And the main thing to note is what is the misprediction histogram? And without just kind of a regular support vector classifier, without sort of doing any sort of enhancement to it or finding that pass-fail boundary, we get a much larger number of mispredictions without the enhancement than with the enhancement. And you can see just the misprediction histogram on the right of, okay, once we enhance our model and get that better understanding of the pass-fail scenarios, we get much fewer mispredictions. And as a result, we can simulate this with much fewer simulations. We can run much fewer simulations. And just for comparison, I ran no machine learning whatsoever, ran all of the cases, simulated all of them, and virtually get the same results. Okay. So this is important because we're trying to avoid simulations. When you have doing lots of predictions and you're having to simulate some of them, obviously the predictions take much less time. So simulations kind of get in the way, right? So trying to avoid those simulations help us get through the Monte Carlo process quicker and allow us to do more samples. So here's another case, and this is on this slide, there's sort of three things to note. All I did was I just bumped the supply voltage slightly higher, like 50 millivolts, 100 millivolts, something of that nature. Delays go down, and keeping that sort of same delay threshold as a pass or a fail, the failure probability also goes down, but goes down a lot. So that's why we need this adaptive approach, is because designers may be running under different voltages, and they just want to run the tool. They don't want to have to worry about, well, how many samples should I tell the tool to run, or how many simulations should I run? We just want to run the tool. So in this case, we ran about 100 million simulations. We had fewer simulations with the support vector classifier after we did our enhancement step. And the thing that I'll kind of note is we are still doing a lot of simulations. We are checking these extra simulations in both cases. We are being very conservative and checking any condition or any prediction that has predicted to be pass that might be close to a failure according to our scores, because we don't want to miss any failures. I would much rather have the designer call me and say, oh, we're running lots of simulations, but we're capturing all the failures. That's much better than running few simulations and missing failures, because that's the crux of the problem, is the designers want to know how often the circuit fails and what kind of conditions caused a circuit failure. So as my last slide, so we've talked about this Monte Carlo process using our kind of two-step support vector classifier, where we separate out the training step from doing the actual Monte Carlo analysis. As a result, we can adapt to different kinds of scenarios, what kind of criteria the user has specified, the actual failure probability. And the nice thing is we can run just Monte Carlo and just adapt to mispredictions, adapt to what kinds of failure probabilities we're actually seeing based on the designer's specifications. And so it really kind of frees up the designer from having to kind of worry about the tool and focus more on what's causing their designs to fail and how can they improve those. All right, thanks very much for your attention, and I'll take any questions or comments.
Thanks, David, for the great talk. Let's see whether we have any question from the audience.
Hi, David. I have a question.
Sure.
Hi, David. This summer, I was working as an intern in the Cadence circuit simulation team, and my project was fast Monte Carlo yield analysis, so which is kind of similar to this project that you are doing.
Yeah.
I have a question. First question, when you apply the support vector machine to locate the critical samples and cache extra simulations, is that an iterative process or just a single run?
It happens on the fly because in a sense, what we do is, as you can imagine, it's a big parallel job. So we are sending out kind of blocks of Monte Carlo samples, and with each block that's coming back to us, we're looking at like, okay, how many mispredictions were there? Where were they located? Do we have to adapt? How many more passing scenarios do we need to simulate? Do we need to adjust our cache size? So we're doing that kind of all on the fly. And as criteria get solved, kind of, we determine their failure probabilities, we can start adjusting based on, what remaining criteria have to be sort of evaluated.
And also the parameters for the support vector machine also be updated after each process.
No, that's a key point, is the models themselves remain constant. So we're not updating the features. Is that your question, whether we're like updating the features?
Right.
Yes, we're not updating the features because the main issue is if we, the reason of doing the sort of the first step is we're trying to find all of the conditions that make the circuit fail. What would really be bad is if we did not understand all of those conditions ahead of time, and if we like retrained the model during the Monte Carlo process, we might have to go reevaluate our last, 500 million samples looking for some new failure process that maybe we didn't capture, for the first 500 million samples. So that's really kind of the importance of doing the two-step process, doing the training first, is because we're really trying to find all of the possible scenarios that could cause.
Right. Okay, thanks very much. We can discuss later.
Yeah, you're welcome.
Thanks again for David's great talk. Due to time limit, maybe we can move to our last presentation in today's technical session. The last one will be presented by Martin, talking about the NM-based online estimation for full chip temperature and rate of temperature change. Martin, I'll pass the time to you.
So yeah, thanks for the introduction. I'm Martin Rapp. I'm a PhD student at the Karlsruhe Institute of Technology, KIT in Germany. And let me just jump right in. So temperature is the main limitation of multi-core performance. This is especially since the failure of Dennard scaling caused the on-chip power densities to increase. And as we all know, elevated temperatures can damage the chip, which is precisely the reason why virtually every modern processor has some protective measures against it. They have, for example, DTM, dynamic thermal management, built into the hardware and firmware. What this DTM does is, once a thermal violation is detected, it will very aggressively throttle down the core. And this throttling down significantly reduces the performance of the processor, which is actually not required. I mean, in many cases, you don't need to throttle down to the bare minimum frequency. You can throttle down a bit and still avoid the temperature violation, still avoid the temperature violation. So what we need really to do is we need to avoid the DTM triggers, that DTM is triggered and aggressively throttles down the chip. So we need to proactively avoid temperature violations. How can you avoid temperature violations? For that, you need to know two things. First, you need to know what is my current temperature. And this is not just a single value for the whole processor. No, this is actually a image, a 2D image that for every location on the die has the information how hot is the chip at this position. Knowing the current temperature, the absolute temperature, is not enough. Also, what is also required is knowing how the temperature is currently changing. And this is also, again, a 2D map of the whole chip, indicating which, for every position, how does the temperature change? Does it go up? Does it go down? How fast does it go up or down? And this is exactly what we do in this work. We develop a runtime technique to estimate both the absolute temperature, which is the full 2D map, and the rate of change, again, the 2D map. We have designed a neural network topology with 2 independent branches for 2 feature types. I will go into detail on that a bit later. So first, let me walk you through how the technique works. We start with a current estimate of the on-chip temperatures and performance countermeasurements. These two are both passed to a neural network that predicts us from these measurements how does the temperature change, which is again this 2D map, indicating, for example, that in the bottom left corner here, the the temperature would increase, while in the remainder of the chip, the temperature would not change at all. Having the current temperature and the rate of change allows us to combine the two to get the next temperature estimate. And this is what we can provide to the proactive thermal management together with this information, how does the temperature currently change? And then the cycle repeats. We get new performance counter measurements, we have a new estimate of the temperature, we can pass it to the network again, and thereby iteratively or continuously update our temperature estimate based on the performance counter measurements. I would like to share with you 2 interesting insights into the technique. First, in order to train such a network to work on full thermal maps, we need some training data on that. And it's very interesting that the second to last talk before me also used a similar setup with an infrared camera, as shown here on the picture, that allows us to obtain the very accurate information about the temperature at the temperatures of the die. With this setup, we record roughly 2 hours of training and test data. The second thing that I find interesting here is that our network has 2 very different features. We have the current temperature estimate, which is an image, which is processed usually with convolutional layers, and which is also what we do here. And we have the performance counters, which are, after pre-processing, an uncorrelated set of values, which you would process with fully connected layers, and which is also what we do here. So overall, our topology has these 2 branches that are only shared a bit later. And then the output of the technique would then be this 2D image of the rate of temperature change. If the model topology overall resembles a bit an autoencoder structure, where we have the convolutional, the fully connected, and the deconvolutional layers. So it has some resemblance here. Looking at some results, the first interesting thing, obviously, to look at is the model accuracy. How well does the model predict our temperature changes? And the graph here shows that this red line, the prediction, actually matches pretty well the measurement, where the main trends are predicted correctly, and there is some noise in the measurements that is not reflected in the model, which is okay. So overall, our model has high accuracy. However, if we build the full technique, if we use the model in the closed loop, where every output of the model is then fed back as the next input, we see that the predictions do not match the reality anymore. We did investigation why this is the case, and we found that the reason why it happens is that over time, the patterns that we feed to the network deviate from the patterns seen during training. And this is something that you would, even with the splitting into training and test set, would not observe, this is something that you only observe in the closed loop experiment. And this brings me already to the conclusion. So we have in this work developed a technique to estimate the temperature and the temperature and its rate of change. We have this neural network topology tailored for our specific features that we have. And we found that while the model is actually fairly accurate, the closed loop predictions do not work. And we have also some ideas how to fix that, but I guess I need to skip that in the interest of time. That concludes my short presentation. Thanks.
Okay, thanks Martin for the great talk. Let's see whether we have any question from the audience. In general, I really like the idea for the whole system. So if my understanding is correct, so that the training can be kind of time consuming because we have to measure the ground truth for each state level by level.
Not sure whether I got your question correctly. Do you mean it is time consuming to gather the training data, or do you mean the training itself would be time consuming?
Compared to conventional training, obtaining the training data here can be time consuming?
Yes, I mean, obviously, you need to run workloads on the system and record them. In our case, we had the 2 hours roughly of workload that we recorded, which takes then also roughly 2 hours to execute.
Yes, yeah, that's a huge workload, quite impressive.
Hi, Martin.
Hi.
Hi, Martin. Well, actually, the setup in our lab is actually inspired by your ISOPAD paper in 2015.
Ah, I see. Okay.
Yeah. And I have a general question for your slide page 5. When you show page 5, when you show the comparison between the measurement and the prediction for the open loop, and you mentioned that the error, the relatively large error occurs when the temperature has big spikes, right? At the spikes. So do you know the error is acceptable at the spikes?
Okay, let me try to answer that question. So in the end, it does. If you have a very short misprediction in the rate of temperature change, maybe you miss a spike up or you miss a spike down. This does not cause too many problems because the spikes are short. So while there is for a short time a strong temperature gradient, it's only short, and the next spike will come that balances it out. To investigate exactly this question, I also plotted these curves, the integration of these curves over time, to see whether there is some structural error, so to say, so that it always misses the spikes up and never misses the spikes down or so. And this was not the case. So here, did it answer the question?
Yeah, pretty much. And I'm also thinking maybe the spikes for the real measurement, maybe the sensor noise may not be really the spikes. They may just be noise.
Yeah, it may be the case. Yeah, true. Yeah.
Okay, thanks very much.
Okay, let's thank speaker again for this great talk.